Hi everyone, welcome back. My name is Ananth, and today we're going to be talking about aligning LLMs using RLHF. So to start off, we'll define the alignment challenge and what alignment really means. And this is basically imperfections that exist in LLMs as a result of its training data and training process. So inherently, when you ask an AI something, controversial or something that it doesn't know about, it'll either hallucinate or produce something that is extremely biased, which is something we want to align more to human behavior and prevent from happening. So RLHF stands for reinforcement learning with human feedback. And this is how we're going to incorporate more and more human preferences into the loop to ensure that we have guardrails or guidelines for our LLMs to act on. First, we're going to fine tune our base LLM on some labeled human data in order to get our starting point just a little bit higher, and we can optimize more effectively from there. Then we'll define our Bradley-Terry model, which allows us to map human preference data into reward probabilities. As you can see right here, we define this probability that we prefer this response to another for a certain prompt X is equal to the sigmoid of the reward of the preferred response minus the reward of the dispreferred response. Next, we'll collect some comparison data in order to learn more preferences. And for a given prompt, we're going to generate n outputs. Our human labeler is going to rank these outputs from worst to best in order of the human guidelines we're trying to teach. And we'll use that data to train a reward model. Using this reward model, we're going to optimize our original policy against, or our original base LLM against this reward model using RL. For a given prompt, the flow looks like you generate an output, collect a reward, or calculate a reward, and feed that reward back into the loop to update the policy accordingly. In our optimization objective, or our loss function that we're trying to optimize, we're looking to maximize the expectation of the reward minus the KL divergence. And this term right here basically just says we don't want our optimized policy or our new policy to stray too much from our baseline model. And now that we've defined what we want to optimize, we have to get into the details of our implementation, bringing us to our first strategy, which is proximal policy optimization, or PPO for short. In PPO, we start with a prompt queue, feed it into our policy model, get an output, and feed that output to our reference model, reward model, and value model. The reference model and reward model together with the KL divergence term will compute the reward, and our value model will compute the expected reward for the same question output pair. And together, we're going to compute the generalized advantage estimation, which basically at a high level is the actual reward minus the expected reward. After getting the advantage, we're going to feed this back into our value model as well as the policy model. So if you recall from last week's lesson, we talked about the actor-critic architecture. And in this case, we have our policy model, which is our actor, and we have our value model, which is our critic, giving direct feedback to update the policy model's parameters. In math, we see this loss function as the expectation of the minimum of RFT times the advantage compared to the same RFT but clipped to this range 1 minus epsilon, 1 plus epsilon times the advantage. And now we can see these here together. So while PPO is a great strategy for producing stable updates based on human preference data, we still have the bottleneck of RL and training this value model, which requires a lot of compute and overhead. So to solve this, we define our next solution, which is DPO, or direct preference optimization. In DPO, we completely drop reinforcement learning, our reward model in general, and switch to a completely supervised learning problem. And it ends up being just a binary classification between your preferred and dispreferred response using some neat algebra. So in DPO, we first start off with our loss function on our reward function. So here we have the negative expectation of the log sigmoid of the reward of our preferred response minus the reward of our dispreferred response that we saw earlier. Next, we transform this reward function to reflect the policies where we have just some parameterization of our reward function. And you might notice that we've removed the need of a reward model incomplete. So this brings us to our final loss function on our policy directly, where we define the negative expectation of log sigmoid of the beta times the reward of your preferred response minus beta times the reward of your dispreferred response, except your reward is completely defined by your log of the policy you're trying to train versus the policy of your baseline model. This completely removes the need for reinforcement learning and training the reward model in general, and is a much more efficient strategy. However, it does, in some cases, sacrifice some of the stability that we found with PPO, bringing us to our next strategy, GRPO, or Group Relative Policy Optimization. In GRPO, we follow a similar framework to PPO, except we get rid of our value model completely. The flow looks like, for a given prompt, we generate G outputs using our policy model. We feed these G outputs into our reference model and our reward model, generating G corresponding rewards. Using group computation, we compute the corresponding advantages for all of these rewards and feed this along with our KL divergence back into our policy model. And we use group relative rewards instead of the learned value baselines that we had in PPO. So our objective function to start off is the expectation over G outputs. And here we'll see that it gets a little bit more complicated, a lot more terms, but once we break it down, it's not too bad. We notice that first we have 1 over G to the sum of I equals 1 to G. So we're just taking the average over our G responses. This term right here is identical or nearly identical to what we had in PPO, where we're taking the minimum of our policy from the current policy we're training for a given output over the baseline model times the advantage. And we're doing the same clipping for 1 minus theta, 1 plus theta. However, you'll notice that our KL divergence term is being added at the end rather than prior and directly into the rewards. If we look back at our GRPO right here, we notice that the KL divergence term is not going towards the computation of the reward, but directly back into the policy model. So it's just acting as a regularization term. Now, to put it all together in a nice way, we have GRPO, similar to PPO, that takes the average over G responses. We compute the same probability ratio from PPO, and our advantage looks a little different since we don't have our value model. Instead, we're computing the advantage from a current reward compared to the mean over the standard deviation of all of the rewards computed. So one inefficiency is that we have to wait for all the rewards and outputs to be computed to do GRPO. Next, we have the same 1 minus epsilon, 1 plus epsilon bounds, and we know that we subtract the KL divergence term here at the end rather than directly into the reward. Now, to recap everything we learned today, we talked about alignment and how we need to align large language models with human preferences, and we go about this using RLHF. We talked about PPO, which is our actor critic RL method that uses a reward model to implement RLHF and take care of that alignment we want. We talked about DPO, which is a supervised learning method and an RL-free way to go about alignment. And we also discussed GRPO, which is a value model-free or a critic-free RL strategy that uses group rewards. That's all for today, and I'll see you guys in the next one.
Thanks for watching.